Hi everyone. So welcome to this video. This video is about inclined manometer. And we just basically wanted to give you some practice on manometer problems. We have done a couple of them in class. And you also have an homework one problem too that focuses on sort of this idea of manometers. So let's go into this. And the question is that we have a manometer, but the usual manometers are straight vertical, right? This is an inclined manometer where the arm that you see on your right hand side is inclined, right? And this is vertical. And you have been given that the inclined manometer is at an angle theta with the vertical side. There's an angle theta here that this angle is theta. And what you've been asked to find is, the question you've been given is find the value of L in terms of H and theta. Okay, it's a simple problem, but I just wanted to give you that practice so that you can start to think about this problem a little bit more deeply. So what this problem is really doing is saying we have a manometer, we have filled it with a fluid, let's call it water, and you have been asked to find the value of length L in terms of H and theta. Okay. So naturally, because of the way we have shown here, the gravity is in the vertical direction here. So first things first, and this is a manometer, and we are not basically saying that the water is moving or anything like that. So this is a hydrostatic problem. So remember always, this is a hydrostatic problem. Okay, so hydrostatic problem. And what we essentially need to do here is to remember that we have discussed different formulas, but let's start the common approach that we're doing, which we've been doing. So we'll find a vertical line, and because it's obvious in this problem that we have been asked to find L, we'll create a sort of a horizontal line here and here, right? So let's call this point 2, let's call this point 3, and then we have this point 1, and we have this point 4. Okay, so we create these points in any manometer problem, and we start to use the hydrostatic formula that we have discussed in class. So how do we do this problem is that we'll say, well, P1 we know is at the water air interface. So P1 is P ATM. Okay, then P2 is P1 plus gamma times H. Okay, so remember that we use this formula of gamma times H if you're going down. Okay, so we are going down. So I have this. Okay, we are going down. So it's gamma 1 time plus H. Then P3 is actually just equal to P2 because we are at the same height. We are not changing the height. And so we go one step by one step. So the same height. So this is P2. And then P4 is P3 minus gamma. And so what should be the height here? So what should be the height in case of, like, because we're going from 3 to 4. So remember, the height is this height here. And I'm going height. I'm not going the length. I'm going in the height, vertical direction. So if this angle is theta, this is L. So this becomes L cos theta. Okay, so minus gamma L cos theta equal to this. And then I also know, so gamma L cos theta. And I also know that P4 is actually equal to PATM, right? Because that's again at the air-water interface. So essentially, we basically go from, like we did in the class, you go from one point to the other point, and you can simply do this. And what you can find this in this problem is that if you substitute everything, so P3 is P2. So I have, this means that this is equal to P2 minus gamma L cos theta is equal to PATM. P2 then it becomes P1 plus gamma H minus gamma L cos theta is equal to PATM. And then P1 is equal to PATM plus gamma H minus gamma L cos theta equal to PATM. So this goes away, this goes away. So I get H as L cos theta. Okay, gamma H as L cos theta. So what I'm basically trying to do and trying to kind of inculcate here is, first, you always have to take the vertical height. So remember, if there is a length and inclined angle, you can take a trigonometric vertical height. You will do something similar in your homework one problem too. And more importantly, get sort of this practice of, correctly signing the sign. So note that we did a minus here because we are going upwards, and a plus here because we are going downwards. Okay, so remember that sort of relationship. So you get H is L cos theta, but that's not just the answer. Let's also try to figure out if it makes sense. So if my theta is 0, if theta is equal to 0, then I get H is equal to L, because cos theta of 0 is 1. And which makes sense. If I have a vertical tube, if both the tubes are vertical, then this inclined length becomes equal to H, right? If theta is equal to 0, then I get H is equal to L. What happens if theta is equal to pi by 2? If I have theta equal to pi by 2, then H is equal to 0. So that's, I should maybe write L is equal to H. So maybe let's do this. If theta is equal to pi by 2, then I'm getting L is equal to 0. So is that correct? Like if I have a angle such that it's now almost horizontal, this tube would look like something like this, right? That's why the angle with the vertical would be pi by 2. So how is this correct answer? So this is not correct in this case. Particular case is because if I have something like this, the tube water will start to flow. And so remember, then I will not be able to satisfy I will not be able to satisfy the hydrostatic condition. Okay, so just wanted to show you that this answer works only if it is a hydrostatic problem. If it is like the sin theta equal to pi by 2, you just don't have hydrostatic conditions anymore. The water will start to flow. So you can also make sense of some of these answers physically. Okay, so the main idea behind this video was to show you what happens. You go from 1 to 2 to 3 to 4. You use the formula of plus gamma H, and where H is the downward direction. So if you're going upward, it's minus. And also use the vertical height so that in case there's an inclined manometer, you can get the right answer. All right. With that, I'll see you in the next video. Have a good day.